lot of fancy words there. Translunar injection orbit, just fancy speak. I just pulled that from a movie. Spacecraft has to fly through a point between the Earth and Moon where the net force is momentarily zero. All the stuff that's talked about there is true, and those words, I mean, that's what they would say in the movies. Of course, I don't really know what they would actually say. The idea here is pretty straightforward. The way they did it in the days of Apollo were different than probably how they're going to do it now. The new rocket looks a little different, but the way they did it in the days of Apollo is they launched your rocket from the Earth, and immediately the booster sent it on a path that would take it to the other side of the moon, and they would get into orbit around the moon. With the idea being that after a couple of orbits, if they were stable, they would change their orbit a little bit around the moon and get as close as possible, detach the lunar lander, drop that to the planet. An astronaut would stay with what was called the command module. He'd stay in orbit so that if the astronauts on the planet ran into trouble, he could just leave them, because that was part of the process if things didn't work out. But if things went well, then the astronauts came back from the moon and redocked with him. They ejected all the parts they didn't need, then fired the rocket from the command module, take them back to the Earth. There's a point in the middle here somewhere where the force of gravity from the Earth is equal to the force of gravity from the moon. And it is an unstable Lagrangian point because you can't actually stay there. Although the net force is zero for that instant, to stay in an orbit at this location would require an unbalanced force towards the Earth. So it's not a stable point. So you can fly through it, and they do fly through it. But remember, this is a bit of a... we're playing easy with the rules here. None of this stuff is stationary. All this stuff is moving. So they were in this point for an instant where the net force was zero. That suggests, though, that there's the force from the Earth on the spacecraft in that direction, and the force from the moon on the spacecraft in that direction, and they had to be equal. That's why the net force would be zero. So mass of Earth, mass of spacecraft G over separation distance R squared. And this separation distance I'm using a pointer that I made up, or a name that I made up. I'm going to call it RS, represents this distance. Right, it's going to represent the separation distance between this point in space and the center of the Earth. At the same time, there's going to be a force from the moon on the spacecraft. But in this case, I could put a different separation distance if I wanted, but that gives me two variables. And if I have two variables in one equation, there's not a whole lot I can do about that. But that would be, say, this distance, Rm. Now, they said with respect to the Earth in the problem. So I am aware that this separation distance is 384 times 10 to the 6 meters. So Rm equals 384 times 10 to the 6th minus Rs. You have to make up some variables to use here as placeholders, but you're supposed to solve for one of them. And you do have some known values. This is the value I gave you in class, or you could have looked it up in class. Or I'm sorry, could have looked it up out of class. Either way, I'm going to replace that R for the moon with something that I could then solve for a single variable that I could use to solve. I will point out that some things cancel out here. Mass of the spacecraft and G. They're present in both. So you need to find a way to solve this for RS. One of the things I would consider doing is maybe flip both sides and write this as RS squared times mass of moon over mass of Earth equals 384 e to the 6th minus RS squared. I'm just trying to get the binomial by itself because you're going to have to deal with the binomial. And there's nothing great about this, you have to solve this for RS. And this is where I'm going to tap out because there's no reason for me to do the quadratic formula for you. I'm just going to do a little bit of due diligence in that I will set up what I think is what you need to do. You have a value for all the things here. So plug it all in. Mass of the moon, 7.3 times 10 to the 22nd kilograms. Mass of the earth, 5.96 times 10 to the 24th kilograms. Those were all given in class, or you could look them up. But I'm not going to do the the quadratic formula for this. I didn't actually. I just plugged it into Wolfram Alpha and had it pop out the answer for RS. You will get two answers here, and be careful. One of them is wrong. Mathematically, it's a quadratic, and it will produce two answers. But one of them lies outside of the distance between the Earth and Moon. That's the wrong answer. It has to be between the two. So please only choose the one that is between the Earth and Moon. Any questions about that? All right. So in the first instance of this drawing, you're supposed to draw what the new orbit would look like and describe it qualitatively. I'm going to be as clear as possible. If yours varies in any significant way from what I draw here, you will receive no credit for the drawing. They are very specific, and they are looking for specific mistakes that students will make in doing this drawing. So remember, all orbits are circular or elliptical. And if elliptical, the object they are orbiting has to be at one of the focuses. So if you're traveling too fast for the circular orbit at this orbit, that means you're going to travel outside this circle. So in considering what to draw here, you're going to need to draw an ellipse. But basically, it's got to be elliptical, and you have to draw it in such a way that they would travel outside the circle. So any ellipse drawn in such a way that your velocity takes you outside the circular path, places Jupiter at one of the foci, and makes this point the closest point, and a point directly through the center on the opposite side, the furthest point, is correct. That's how it has to be drawn. The most common incorrect answer, and there's a bunch. See if I can back this up a little bit. One of the most common incorrect answers is to draw it something like this, like an eyeball, because it still has qualities that sound like it's right. It's elliptical. It shows it going faster because they say faster at that point. But obviously, Jupiter is not at one of the foci, but this is one of the more common incorrect answers. And they're looking for you to make this mistake. So let's try not to. That's the correct answer for this one. Now, they go on and indicate that when the satellite is at the desired altitude over the equator, its velocity vector has the correct direction, but the speed is slightly slower than the correct speed for a circular orbit of that radius. Well, you're going to have to adjust your ellipse. And unfortunately, you don't have a little elliptical tool, on the exam. But you have to adjust it so that you would fall inside the circle, right? Your velocity is not great enough for a circular path. You're going to fall inside the circle this time. And in doing so, you need to show that your entry point is at the furthest place away from the planet, and that directly across from there, you have your closest approach to the planet. with your planet at one of the foci or appearing to be at one of the foci. That's how it has to be done. Again, a super common incorrect answer here is for students to, see if I can do it, draw it like that. And yeah, wrong, right away, you'll get no credit. So if you're trying to figure out just how much energy it takes, the whole idea here is that you have to bring your energy to zero because you currently have negative potential energy due to being trapped in the Earth's gravity well. So we just put in this information, work it out. That's how much kinetic energy you need to have. Now, if you want to find out how fast that is, well, you take this value and set it equal to 1/2 massive u velocity escape squared. And that's going to be, again, whatever the result of that is, 5.96 e to the 24th times 80 times 6.67 e to the negative 11th divided by 6.37 e to the 6th. So clearly mass of u is 80. So the 80 part cancels out here. Multiply it by 2 and take the square root. That'll be the escape velocity. When you work that out, you get something like 11,000 something meters per second. Now, that truthfully doesn't get you escaping the solar system. It would get you away from the Earth. But now, as you get out to this point, say, and you're leaving the Earth and you've got enough, you're just being pulled into the sun. So the sun being over here and you being a distance 149.6 times 10 to the 9th meters away, your job now is to figure out the escape velocity from this point. You could include the amount of kinetic energy you already have, or you can decide not to include the amount of kinetic energy you already have. It will make a difference in the problem. But they ask what the escape velocity is from here. So I think the best way to answer that is to just figure out how fast you have to be going. And then you are already traveling 11,000, you'll have to increase to whatever the difference is to escape the sun. So I found the escape velocity from the sun at this location. Well, the total energy again has to be 0, but we're talking about mass of the sun, mass of u, g, over your distance, the Earth-Sun distance. This is all negative, and I have to add my kinetic energy to it. That's going to be 1/2 mass of u v escape the sun squared equals mass of the sun, mass of u, g over the separation distance between the Earth and sun. Cancel out the mass of u. Everything else is there. You need the mass of the sun, which is 1.99 times 10 to the 30th. So it's like 40-something thousand meters per second. You're already going 11,000. You have to be going more than 4 times that speed to get out. That's not easy. It's a lot of energy. A lot of energy. You probably wouldn't use a rocket. You'd probably use something else. You'd probably do some fancy flying to do it. That's outside the scope of this course, but that's what they did. They would pump they would pump it kind of like a swing, get flying towards the sun, and then at the last minute veer off a little bit, use the energy of falling towards the sun to kind of slingshot them faster outside the orbit. By manipulating their path in and path out, they can get a gravitational slingshot effect. I don't know how it's done. That's just the movies talking, but that's what they did for the Voyager space probe, so it must work. Next question. They also did it for New Horizons. They've done it for a lot of spacecraft that have gone out to the outer solar system. Okay, so again, for this problem, part A has really nothing to do with the mechanics of this problem. It has everything to do with seeing if you understand where the expression for potential energy comes from. And they're going to be looking for understanding that you are starting with the technical definition of work, you're starting with the technical definition of potential energy, and you understand that you are integrating the force of gravity between two objects as started from a place where the force on the object is 0. That's what they're looking for in your activation of this problem. So we want to give that to them. You don't have to do the integral. The answer's been given. So they're not asking you to execute the integral, just merely set it up. All right? And yeah, A and B, all that, they're not distractors. You're probably going to use them later, but you don't need them now. Does anybody else want me to continue this problem or not? All right. Just a statement. So I don't know if you need it. It doesn't look like it. So in this problem, they have Earth here. They have shown a elliptical orbit where Earth is at, or something like that, where Earth is at one of the focus. Try to make it look a little bit like that problem. And then they've indicated that there are 2 important radii. This one is A, and this one is B. And they say that it has a velocity of v naught at point A. So at point A, our satellite has a velocity v naught. And their question is, what is the magnitude of the angular momentum of the satellite about the center of the Earth when it is at A? L equals r perpendicular mv. So for this, that's just going to be A m v naught. That is the angular momentum at that position. It's got a velocity that is perpendicular. There are only 2 places where you can use r perpendicular to calculate the angular momentum. This is one of them. You could do this another way, but I would highly not do it the other way. The other way is to consider angular momentum I omega, but this object does not have a uniform omega because r is always changing, so I wouldn't do it this way. Mathematically, you may get what appears to be the right answer, and instantaneously it would be, meaning you'd put in that it's a point mass of mass a squared for its moment of inertia, because it's located at a distance a away from this axis of rotation, and omega would be for that instant VA over A. All of that would be true and you would get the right answer. But I think your test graders would call into question the idea about this because omega is changing all the time. And this would still be constant because R is also changing all the time. But if you don't know that and don't understand the relationships, I would stick with the point mass calculation as your safest bet. Let's see, there's more to the problem. Determine the velocity of the satellite as it passes point B in its orbit. Angular momentum has to stay the same. So the angular momentum at point B, which is over here, it clearly should show me a velocity that is smaller. But that's because as it gets further away, the force of gravity is acting to slow the object down. These are all qualitative things that you should be able to say should they indicate, justify your answer. That makes sense? I mean, be able to. So there are 2 things, or there's 3 things that can be brought to bear here. A qualitative description of the force of gravity acting with a component that slows it down. There is the clear indication that the net torque is 0. So angular momentum at point B has to be equal to the angular momentum at point A. That's another way to do it. The third way to do it is probably the hardest, and that is that energy is also conserved in this orbit. So the total energy at A has to be equal to the total energy at B. But energy is a lot more difficult to work with. So I would really narrow it down to angular momentum. It is the fastest way and the most direct way to do this problem. So we know that these 2 have to be equal. This one is A m v naught. This one is going to be B m, velocity at point B. The mass doesn't change, cancel out the m's, and the velocity at B has to be the ratio of A over B times v naught. So I think that's all of that. You just said C and D. Is that it? So it's in a circular orbit. The object is around whatever planet. So, and they tell us that the radius of the orbit is 2r. So, doing my best, but that's what I think it should look like. That's disappointing. The orbital radius is this distance, which is 2r. The object is here, going with some velocity, and we are told it is a stable circular orbit. So the kinetic energy of that orbit requires that we find the velocity of the spacecraft. So the only way we can get that is probably by using net force and centripetal acceleration. So net force equals MAC. We can do this because it's a circular orbit only. So capital M, lowercase m, g over 2r squared equals mass of the satellite. That's what's going around. So we put that in the other side. Make sure you keep remembering that. Times a, because one of the biggest mistakes you guys make is putting the wrong m down here. You'll put the mass of the planet or the mass of the sun or something silly there. So make sure you know what it is that's doing the orbiting versus what it is that's at the center or in the focus. And this is going to be the velocity that we're talking about divided by 2r. So cancel out the 2r's, cancel out the m's, and solve for v. And we get the square root of capital M, capital G over 2r. Okay, this is the velocity. Now go back to find the kinetic energy, and we'll get 1/2 m times mg over 2r, or mg over 4r. Any question about that? All right. So the next part of this is to find the total mechanical energy of the system relative to a point infinitely far away. Again, fancy talk for indicating that the total energy will be the gravitational potential energy plus the kinetic, where the gravitational potential energy is based on mg over r, in this case 2r, plus the kinetic energy that we have mg over 4r. Add those together, and we'll get negative mg over 4r. Two common denominators and add. This has to be negative. So if you're calculating an orbit's energy, it will have to work out to be a negative value, regardless. Unless you have enough velocity to escape, and if you did, you would no longer be in orbit. You would have escaped. So anything that's in orbit doesn't have enough kinetic energy to escape. So thus the total energy has to be negative. It's the way in which we've chosen to do this, and it mathematically works. So I'm going to draw the picture a little bit. I think that as we look at these, well, I don't really know what's going on, but I'm going to take that away. Okay. So that look good? Looks like the picture. They have a couple of labels here. Let's get the labels in place. There is a label from the center of the Earth to here, and there's another label from the center of the Earth to here. And let's see, RA, RB, and they've drawn some arrows here, so VA, and I'm going to be more diplomatic and draw this arrow smaller, because you should already know, even though they don't want to give it away, you should already know that it travels slower when it's further away and faster when it's closer to. So should it come up, you should be very capable of dealing with those differences. You said you don't care about A and B, you wanted C. Determine the speed, VB, of the spacecraft at point B. And looking at the information provided, they have given me values to use for RA and values to use for radius of the Earth, velocity of the Earth, and VA. Do they give me RB someplace? Yes, RB. So, all right, so I can determine it, sure. The thing that we know about an object that is in orbit, several things that you should know. I'm going to do a quick rundown of the things that you should know. First, we're dealing with elliptical orbit. So these are the things that are true about an elliptical orbit. Some of these things are true about all orbits, some are not. So I'll differentiate. But if you're trying to study and you want to know, especially like in the multiple choice version of this test question, angular momentum is conserved. So the value for the angular momentum, which I will put as an L, which is R cross MV. And I'm writing it this way specifically because the angle is changing all the time as it goes around, but that has to stay the same value. So if we write it out like R MV sine of an angle, R, V, and the angle change all the time, but the product stays the same. Also, the total energy of the system stays the same. The sum of the gravitational and kinetic stays the same the whole time. But sometimes the energy is more potential, sometimes sometimes the potential energy increases and sometimes it decreases. The closer it is to the Earth, the larger the kinetic energy is. The further away from the Earth, the smaller the kinetic energy is. But these being the same, that's true for all orbits, even circular. In a circular orbit, though, the kinetic energy and the potential energy would stay the exact same value the whole time because it's never getting closer or further away. And in a circular orbit, R would stay the same value all the time. In a circular orbit, there is a distinct difference, and that is the net force equals MAC. In this one, that's not true. The net force equals MA, where a portion of that acceleration causes a change in direction, but the other portion of that acceleration causes a change in speed. That's critical to understanding this. If we're looking at right here, well, the force from this point is towards the center, but the velocity at this point is tangent. So the part of the force in this direction is the centripetal acceleration. And the part of the force in this direction causes it to slow down. Right? Those are the two contributions to the acceleration. And they're caused by the not unbalanced. They're caused by this force acting on it. So these are just things that you should be keeping in mind for orbits. This problem, though, is actually solved relatively easily. You have a choice on how you solve it. You can use either conservation of momentum or you can use conservation of energy. I'm going to show you why you might want to use one versus the other, okay? By setting up the harder one first. So the harder one to do would be the one where energy is conserved. To set that one up, remember, you're going to need mass of Earth, mass of spacecraft, G, over, and we're comparing two places. So we'll say this is RA, which we know, plus 1/2 m spacecraft VA squared. All right, that's the total energy, the kinetic energy plus the potential. That would have to equal minus mass of Earth, mass of spaceship, G over RB, plus 1/2 mass of spaceship, VB squared. Energy is conserved. Now you can plug everything in that you know, which is the velocity at A, R at A, and RB, and solve that for VB. Or they chose this point and this point that gives us a significant advantage in this. This will work regardless of where the object is in orbit. It will work anywhere in orbit. However, because they gave us those two parts, they gave the specific points in orbit where we can use our perpendicular MV to calculate the angular momentum. We don't have to know the angle because the angle is 90 degrees at those two places. Because of that, we can say RA, mass of spacecraft, VA, equals RB, mass of spacecraft, VB. So that's only because we're located at the exact apogee and perigee of the orbit. So you can only use this because we're there. Otherwise, it would have to be RA, MS, VA, sine phi A equals RB, MS, VB, sine phi B. We'd have to include the angle, and we have no way yet of really measuring that. You wouldn't need the angle if you did energy because the velocity is squared and it takes care of that. Which one of these is easiest to use? Oh, yeah, this one right there. So much easier. Use that. Is that sufficient? Excellent. All right, so they're asking for the escape velocity if it was at point A. So let me take all of the stuff I don't need and let's get rid of it because this is just taking up space and we don't need it. And they're asking specifically at A. So scrapping this velocity, because we don't need that either, and considering just how fast would I have to be traveling at this location A in order to escape the Earth's velocity or escape Earth's gravity. I remind you, to escape Earth's gravity, you need to bring your total energy to zero because our potential energy is negative. We've got to climb out of the gravity well. At A, my energy is going to be, well, mass of Earth, mass of spacecraft, G, over RA, plus 1/2 mass of spacecraft, V escape squared. And I have to set this equal to 0. And that's it. This is going to tell me what velocity I have to escape the Earth's gravity. So if you just solve this for escape velocity, you'll get it. I'll point out the mass of the spacecraft doesn't contribute here. It would contribute to the energy that you would need. A bigger spacecraft would require more energy. But what velocity you need, we don't need that. So solving this for escape velocity, I'm going to get 2 mass of Earth, G, over RA under the root. To this. An object traveling in a circle, even an object here traveling in an ellipse, you could use, instead of using this to calculate the angular momentum, you could use I omega to calculate angular momentum. If you follow just a quick line of reasoning, you'd have to use I for a point mass, which would be mr squared. And then omega would have to be V over R. And if you do that, you get RMV, just like before. But remember, this is leaving out something. Omega isn't constant. It has a smaller omega when the thing's further away than when it's close. If we were to kind of consider just, the thing that's orbiting, just get a thing. It's going around, it travels slower out here, faster here, slower out here. So if we were to consider what that would mean for an angular speed, well, that's not a good color to choose. Let's choose a different color. It'd be slower here, and then faster here, and slower here, and faster here. So obviously the angular speed would be changing the whole time. So this doesn't easily take that into account. It would drop down to be RMV, but that would only have any meaning at this point or this point where the angle is 90 degrees. It would have no other meaning outside of that. So I would be careful using this for a point mass unless you know a lot about that point mass's motion. It's a classic physics example. It's in every single physics book I say that I've read, but I can't think of a book that doesn't usually have this classic question in it. The concept is interesting. What's actually maybe more interesting and something to keep in mind when we're done is that this would be true even if we drilled this hole, say, over here. It doesn't matter where you drill the hole. If you draw a straight line hole through any part of a planet and work this out, you find that what happens is the same and occurs for the same period, no matter where the hole is. So this one wants to have the hole through the middle. And the idea is that if you drop something here, what would happen to it as it goes through the center? Can you first kind of imagine that this object might mimic simple harmonic motion? It would at least be harmonic, wouldn't it? If nothing else, it would oscillate. At the very minimum, wouldn't it speed up until it makes it to the center? In the center, it experienced no force, right? Middle of the earth, it's being pulled on equally in all directions. Net force is zero. Just like a spring, where if it's going through equilibrium, the force would be zero. And then the whole time it passes that point, wouldn't the force be back towards the center to slow it down? As we have more Earth on the left than we have on the right, and eventually it pop out right here. And if somebody wasn't there to catch it, it'd just fall back through, right? Can you imagine that if you could evacuate out all the air and get rid of all the physics stuff that's, actually going to happen and not let this occur, that it would just keep going back and forth? The point of this question is to try and prove, would it be a simple harmonic oscillator? That's the point of the question. So if you don't see that going in, allow me to just put that front and center. That's the point of the question, is to see if it would be a simple harmonic oscillator, which means from the very start of this problem, and now that you kind of know what you're looking for, the whole point is to try and find the correct relationship that matches d squared x over dt squared equals minus c squared x. It's a simple harmonic oscillator. At least we're going to try and see if it is. To do so, they have a series of steps here to try and chase you through it. And this has been on the AP exam a couple times over the course of many years. I think 3, maybe 2 in 50 years of the exam. They don't offer this on the exam very much. They offer similar questions or different questions that are related, but not this one. Because once you've done it once, you know what to do. The trick is kind of done. It's not like other problems where they can change many things. They really can't. So they say, show that the magnitude of the force on the ball at a distance r less than r from the center of the planet is given by, and they have some expression there. Well, let's see if that's true. That's the hard thing. Understand they're using rho as the density of the planet here. We're not going to, because some things happen when you deal, if you understand what rho is, and you need to understand what rho is. The symbol for rho is this one. So if you didn't know that was rho, allow me to introduce you. That's rho. And rho stands for any kind of volumetric density. Any kind of volumetric density. You've only learned about one kind of density, I think, in your experiences in science. Would I be wrong in saying that you know like mass density from chemistry a little bit? I know that I had to teach it no matter how much I didn't like it. So you learned a little bit about that. The physical properties of matter includes density. And density is just the mass per unit volume. There are other kinds of density. Population density, right? That would be a surface density. Number of people per square meter tends to be how we measure that in the United States. Our cities have a higher population density than our rural areas, where there's more people per square meter than there are out in the rural areas, right? You've heard of other densities. There are 3 different kinds of densities: linear density, surface density, and volume density. How much stuff in a volume, how much stuff in an area, how much stuff on a line. And that stuff doesn't have to be mass. So rho is the general term given for volumetric density. which in the case of this problem would be the mass of the planet divided by the volume of the planet. Oh, so yeah, 4/3 pi radius in this case of a sphere cubed. So when they're talking about the density of the planet, they're saying this, and they're saying it because they say something important here that is not true. That the planet is of uniform density. No planet actually is. Okay, we have a nice chewy center. So should something big enough come by, they might want to take a bite because it's got a nice chewy center. Mars, not so much. More like a gobstopper, nice rocky center. So, this kind of, and I guess Jupiter would be like cotton candy, right? Because it's just nothing but atmosphere until you get towards the liquid part of the middle. So who knows? Could you imagine biting into your cotton candy and finding something squishy and liquidy inside? You would probably not be happy with that. So whoever takes a bite out of Jupiter, that's what they got in store. So, Saturn would float on water. You guys know that? That Saturn is less dense than water. Like overall, the planet. Saturn, Jupiter's more dense than water. All right. So, let's take a look at how we would solve this problem by picking a random place where the object could be. That's what they're trying to do. So I'm drawing this circle. Can you guys see that circle okay? To indicate we are at a distance here, somewhere in the middle of getting to the center. And we'll give this a name R compared to R. They say that we're at a location that is R, where R is less than the radius of the planet. That's what that indicates in the problem. This part you may not have known, and I'm not sure how you would come to understand this. But if you're located here, the only part of the Earth that actually is pulling you towards the center is whatever's contained inside this circle. And I can't prove this to you, but if we were in Kongland, where, it's the hollow Earth, because that's definitely real, because I saw the movie and it was real in the movie, so it must be real. If we were in a hollow Earth and we were anywhere inside of it, I can't explain why this works, because it's too hard mathematically. But if you were inside the shell, you would experience no force of gravity from the planet. Even though you might be closer to one side than the other, if I say just divide this way, you're closer to that upper right portion, but there's less mass in the upper right-hand portion. You're further away from the lower left portion, but there's more mass. And because of the spherical symmetry, it perfectly balances out. So anywhere in there, your net force would be zero. Again, I can't prove it to you. But if you can kind of just look symmetrically at this, you can kind of see that that's probably likely. If you can't, I'm not going to explain why it's true. And it doesn't matter. You just have to believe me, because that's how this problem is done. So this is the only part that contributes to the force on you. I'm saying that because right now, you need to figure out how to write that. How do you write that? Start by figuring out, for the time being, because you're smart people and you're learned and you want to know things. Could you tell me, from what we just talked about, what the mass of that filled in section would be? Because I just gave you the density. So could you write the mass? And I'll write this as I need to have something. How about the mass inside the circle? What does that equal? You know how density works. You should be able to tell me. We done yet? If you don't know how to do it, I'm not mad, but remember, I just gave you this. The density has to be the same everywhere. So the way you use density is to realize that if I take the density here and multiply by the volume inside, that should give me the mass inside. So for those of you who did not know that, I am sad. You could have also just said mass of the whole thing divided by volume of the whole thing has to equal the mass of the little part divided by the volume of the little part. That has to work too, because every piece of this has to have the same density rho. That's what it means to have uniform density. All right, so if you do the math, you get r cubed over big R cubed equals mass of the whole thing. The 4/3 pi cancels out. All righty. So net force equals ma. And that force will be the mass of u times the mass inside the circle divided by g, all divided by r squared, because we are that far away from the center. And that has to equal the mass of u, because we're dropping u down the hole, times a. Good so far? Let's handle something real quick, just to make sure. If we are actually at this point, are we accelerating to the left or to the right? To the left, right? The center is to the left, so the acceleration be to the left. Good so far? What is my displacement from the center? Is it to the left or to the right? Okay, so what you're saying is that my displacement is this way, r is displacement, but the acceleration I experience is that way. Better put a negative sign here. You got to see where this is going, right? I want this. That's what I'm trying to get to. So let's see. I've got this thing to use still. So let's go ahead and put that in there. And I'll cancel out the mass of the thing we're dropping. That's convenient. And I'll get negative mass inside, total mass times r cubed divided by big R cubed times g, all divided by little r squared. And that has to equal a. All good? We're just about done, but do you see that one of the r squared, or both r squared, is going to cancel with the r cubed? So I'm going to rewrite this a little different. I'm going to write this as mg over big R cubed times r equals d squared r dt squared. It's not in terms of x, but it's in terms of r. Works out just fine. Right? R and x are the same thing here. It's a radial distance. That's it. That's got to be the period. It's the value of c. It's the angular frequency. So if I recall, first, they just wanted me to show that F equals minus CR. We showed that right here. That was F equals minus CR. We summed it up here, but we cancel out the M's. Next, although we don't have rho in our answers, you see that we do have rho in our answer. We just canceled some stuff out. It has, on the axis below, sketch what the force of the ball must look like as a function of distance of r from the center of the planet. Well, the force and the acceleration have to be the same. And the force is maximum when we are at the edge. So something like that. But you should be careful because it has in the example r, 2r, 3r, 4r. You should be careful there. Right? Maximum force isn't at 0. So they would probably want me to write this like 0 max. Why would it work today? Still can't write on it. I don't know why. I don't know. So yeah, it did. So as we get closer to R. Oh wait, this is as we get further away. Oh, okay. Just force. Well, it'll always be negative, and it's linear with R until you get here. Because if you look over here, it's just linear with R. But then when you get outside R, well, then it's just the Earth, and it goes down like that. So that's the picture. Let's see. The last thing is, what would the period be? And that's 2 pi divided by c. which has got to be 2 pi times the square root of this stuff. If you do this for the Earth, and you should, it's 84 minutes. That'd be the period. Now, if you're paying attention now after all that long conversation, and by the way, that was only 16 minutes. That means point-to-point travel, 42 minutes anywhere on the planet. Right, that's what that means. Right, you can drill a hole to any place on the planet, drop something in, and it'll pop out on the other side in 42 minutes. Now, I know all of you are going to leave, but the smart ones who really want to hear something, way to lock you all in, huh? We found this orbit. We found it. We found the period of this orbit, one that was right on the edge of the Earth. You should look it up in your notes. It bears a striking resemblance to this. So a geostationary orbit is a geosynchronous orbit. So saying geostationary is saying geosynchronous. And what that ultimately means is that your object stays above the same point on the Earth all the time. So it's actually pretty far out there as orbits go, which is why I'm kind of drawing a really big circle here, because relative to the size of the Earth, it's a pretty far out orbit. But let's my object right out there. So, all right. So, basic setup of the problem. Something to consider is what we are going to find with the stuff we've learned so far is the separation distance. It doesn't ask for the separation distance. So we'll deal with that at the end, but it asks for an altitude. Altitude is defined from the surface to your point above the Earth. That's an altitude. But I think you realize then, if you want to deal with that, you're probably going to need the radius of whatever it is that you're working from. What really matters is that period equals 24 hours. That's what's really going on here. So we have the period. We're working backwards to find the separation distance. Since the satellite, I think we can assume that the separation distance and the radius of curvature are the same. I can either prove the relationship between period and radius again for probably what's the 4th or 5th time, or we can just jump to it. What do you want to do? Well, then that means that t is going to equal 2 pi times the root of r cubed divided by mg. Except in this case, we do have the period of 24 hours, which we do need to convert to seconds. So numerically, this is going to be 24 times 3600 quantity squared divided by 2 pi times 5.96 times 10 to the 24th times 6.67 times 10 to the negative 11th. And this quantity has to be brought to the 1/3 power, and that equals r. I just did the algebra and threw in the numbers all at the same time. I figured that would be okay for all of you. If it's not, just say so, and we can do the algebra first. But this seems like a pretty straightforward question. This is not the answer. This is the separation distance. To get the answer, you must subtract the radius of the Earth, which is 6.37 times 10 to the 6th meters. And my recollection for this problem is that, it's pretty far out there. So I want to say that the separation distance was 42 times 10 to the 6th. When I did the math, I think that's what I got. So yeah, so it says 42 times 10 to the 6th. So I'm pretty sure that's what we're talking about here. Is that enough for you? You're welcome. Again, geostationary, geosynchronous, same thing. When we found this expression, we found it by finding the work necessary to go from a point at infinity to a point on the surface of the Earth. And it's relative to infinity being measured from the center of the Earth, which which is why RE is here. Because we stopped there. The Earth stopped us, and that's how we found that amount. Plus 1/2 mass of u escape velocity squared. And this has to equal 0. And that's it. Solve this for escape velocity. The mass, I mean, if you're trying to find the energy, you find the energy first. So it says what energy is required. So I guess I would just leave this in terms of K and solve that for K to say this is the amount of energy I need, kinetic energy I need to get out, to yeet the Earth. But then I would set this equal to 1/2 mass of u v escape squared to figure out the escape velocity. You work this out and you find out the escape velocity from the Earth comes out to be like 11,700 meters per second. So it's pretty fast. So then, all right, so now you're out there, you're tooling along at something less than 11,000 because remember, this will get you just to the edge of never at a velocity of 0. So you're slowing down. But now, so you're now this distance away from the sun. So in order to deal with the fact that although you're traveling at something less than 11,000, but with enough velocity to escape the Earth, that's just going to mean that great. Enjoy. Or maybe you'll have enough to get you into some kind of orbit around the sun that's stable. Who knows? That all depends on your telemetry. That would probably have something to do with what direction you decided to face when you did this. But if you wanted to escape the sun from here, no matter what your velocity is here, you would have to have the escape velocity required to escape the sun from this location. So again, we would start over again. Your gravitational potential energy relative to the sun plus the kinetic energy you would need would have to equal 0 to escape the sun's field. The truth is, the Earth doesn't really play a role much in this. It plays some because you're close to the Earth right now. You're stuck in its hole. But it's like being in a hole inside a deeper hole. You follow what I mean? So you crawled out of your little hole just to realize that you're inside a deeper hole. You still got to crawl out of that one. So we can figure out how much energy is required to get out of this deeper hole. And that's going to be mass of sun, negative mass of sun, mass of u, g over, in this case, 149.6 times 10 to the 9th meters equals 1/2 mass of u v escape squared. And this comes out to be equal to something like 40,000 or 40, so 44,000, 42,124 meters per second. So, yeah, you got to really be moving. Even if you retain, say, 10,000 of your 10,000 meters per second from your velocity of the Earth, you would have to really hit the old, booster jets to start getting yourself up to that speed. You have an eighth of the amount of energy necessary. Interesting point, though. Probably wouldn't have to do it that way. If you are careful about your selection of vector, you could use the sun and do a slingshot maneuver. You have to adjust your telemetry so that you're kind of like pumping a swing, where you're using the approach vector and careful changes in your telemetry to increase your velocity as you go around. They did this for the Voyager spacecrafts and New Horizons and a few others that they wanted to fling out to the outer solar system or fling out of our solar system. They couldn't give it enough velocity with rockets on the Earth. So they used some fancy flying to kind of whip up their speed. So, and that's kind of how they do it. Imagine like using that force to grab you and accelerate you faster than you approached. And I don't know the mathematics of doing that. And I never looked at it. It's been in all the movies, so I assume it's true. And I know when you look at NASA's web pages for New Horizons and Voyager, they talk about the slingshot effect they use by doing this. Not just these, they've used other planets for steering corrections and stuff like that too. They've also used it for braking maneuvers. So you can use this kind of stuff to help. You do it in reverse to slow you down. And that's another way that like we've sent stuff to like Jupiter and Saturn and use the gravities of these planets to slow down the spacecraft to get them into orbits around those planets to then do some observation of the planets there. All right. So the hole through the center of the Earth problem, yet again. So this video is going to be kind of terrible in that it's going to have this problem twice. But it's got several problems twice, so nobody's going to watch it anyways. And that's good, except for the guy who's going to tell me that I'm shockingly condescending or terribly illiterate. There's no telling. Maybe it'll be something new today. I'm always excited to read those comments. First, this is a classic physics question. It's been asked twice or once in the scope of all the years of the AP exam being given. Because it is a classic question, they don't ask it because every one of these physics books probably has it in there somewhere. It's just very common, and it's a thought experiment. You can't actually drill a hole through the center of the Earth, no matter what science fiction you've been watching. So keep in mind that that's not actually realistic. What's actually interesting, and I bring it up just because it is actually worth exploring in an interesting kind of way, is that you can apply this same idea to a hole not drawn through the center of the Earth, but drawn at an angle that connects any 2 points on the Earth. And you'll get the exact same answer down to the nearest second. Because of the way trig works, the component of the force causing this causes the same kind of activity and does so with the same period as the outcome. So I want to be kind of upfront about, although you can't drill through the center of the Earth, maybe we could drill something like this. I don't know, talk to Elon Musk. He thinks he's got all the answers. There's a point of diminishing returns, though, too. And you can't go that deep. The Earth has a chewy center and stuff like that. So you probably want to find a planet without the hard candy crunch, and that'd be like a gobstopper or something like that. So for those big aliens out there chewing on planets, Mars perhaps might be the better place to go. It's got a center that is not liquid. It's solid. It's all one solid mass. It doesn't have uniform density like we're going to use here, but technically, I guess you could drill a hole through that one. The gas giants, it doesn't make any sense at all, though. Right? What I described them as, they'd be like, Olivia was there, they're like cotton candy with a wet center. Just want you to imagine what that would be like. I mean, how would you feel if you were eating your cotton candy and got partway through and you got a squishy liquid part in the middle? How would you feel about your cotton candy now? You'd probably take it back and complain, or worse, you'd take a good look at whatever was in the center and think, well, I guess I'm done for the day, right? Yeah, I don't know. I don't particularly like cotton candy. Do you, Allie? No, not a fan. But if you could pick any candy, what would it be?
It's chocolate.
Just like plain old chocolate? Really? You didn't say peanut butter cups?
Oh, yeah.
I think chocolate's good too, but once you put a little peanut butter in, it changes the whole formula, doesn't it? I'd say Reese's has figured out the ratio. How many of you would agree with that? They screw it up whenever they turn it into an egg around Easter time. Screws it. Whoa, we have a dissenter amongst us. So is there a better ratio, or is that just not a particularly good candy?
I just don't like candy.
Okay, that's reasonable. So, I mean, if I have to choose between candy and cookies, I go cookies. But I also, there's people in here who between candy and cookies would say neither cake. And then there's the true freaks among us who would say pie. I don't know who you are, and I do not understand you at all. Except unless it's pumpkin pie. I'm okay with pumpkin pie one time a year. But I like pumpkin coffee. And what are you going to say?
Are you a peanut butter fan?
Like, do I like peanut butter?
Yes.
It's the sky blue.
Peanut butter on your burger?
Do I want peanut butter on my burger? Yeah, that's fantastic. If you like reading your television, everything's in Japanese with American subtitles or English subtitles. Okay, back to work. So, and that was only because I've done this before. You drop the object in there. How many can imagine that this object is likely to oscillate? Okay. It remains to be seen if it's a harmonic oscillator or even a simple harmonic oscillator. But I think we could probably consider that as it descends, the force on it is changing. When it gets here, the very center, can we all agree the force should be 0? I'm just kind of using a little power of deduction here. Let's draw a line and a line here. At those two locations, is it clear like there's more mass here than there is here? So at this location, I've kind of indicated right there, it would be pulled, downwards and to the left. And at this location here, it'd be pulled upwards and to the right. So that alone kind of gives me some ideas that it's probably going to travel, speeding up until it makes it to the center, and then slowing down until it makes it, say, here. And if the guy on the other end doesn't catch it, this repeats. All right. That already seems like an oscillator. To prove that it's a simple harmonic oscillator, of course, we have to show that d2x dt squared equals minus c squared x, which is really just saying net force equals minus a constant times position. Right, that's what we have to show. So we've done, this is simple harmonic motion, right? 2 weeks ago, we did that stuff. They have all these extra questions. I don't care about their extra questions. We'll talk about their extra questions a little bit. But what we're really interested in considering is what's happening when the object's somewhere in the middle. So we're going to focus on the object a distance r away from the center, where that r is less than this r. All okay? They tell me the Earth is of uniform density. They use rho as their symbol for density. Rho has a specific use case. Do you know what it is? And the answer should be yes, Mr. Shelton, from at least 2 of you students. What's the special use case for rho? Volumetric density. Not the only kind of density, correct, guys? What are other kinds of density? And we should all know this because all of us went through moment of inertia. So we should know the other 2, but I knew they would know it because we talk about it more frequently and did recently. So what are the other 2 kinds of density? No, types of density, like shapes of density. So we've got volume density, area density. Somebody said it. Linear density. So rho, sigma, lambda. There are lots of ways these are used. And somebody in E&M would likely say that we spend a lot of time with charge density. And I'm glad that you said that. But there's lots of densities. Population density, that tends to be measured as a surface density, right? People per square meter. So cities have more people per square meter than, say, rural areas. So there are lots of densities out there, right? What is the density of the Earth? How would I express it? What's that? Oh, better than that. I've never given the volume of the Earth. What variable sitting on the board right now could we use for this? So mass divided by 4/3 pi r cubed. Yeah, we said we are a sphere, so there we go. I know the flat earthers are just going crazy right now. This is clearly not true. But if it was, then it'd be, I guess, pi r squared, and it would just oscillate through the center of a little disk. I guess that's how those flat earthers think things are going. So this is the part that's not in the problem, and the part I think you have to know to do this. And that's the problem with this whole thing. That you have to come up to a conclusion that's not clear. And the conclusion is that the only thing that contributes to the force of gravity on the object when it is here is how much mass is in this circle. That's not stated in a problem. And I don't know that that's obvious. So let me help you understand this, at least in a small way, by noting that if I were to carve out the center of the Earth so that King Kong will have a place to live, and you were located anywhere in here, unlike in the movie King Kong, believe it or not, the net force is 0 everywhere inside this shell. Now, the folks that are in E&M understand this because of Gauss's law. But Gauss's law could work for gravitational forces in the same way that it does for charge, in that Gauss's law would indicate there's no mass enclosed, and therefore the gravitational flux would be zero, and therefore the gravitational field everywhere in here would be zero. There's absolutely no reason why you couldn't have a Gauss's law for gravity. Now, I can't really explain to you mathematically why this would work because I don't have the math to talk to you about it. But what I would need you to do if you wanted to prove this is that you would have to prove that the force of attraction to every piece of mass in here would balance out due to the spherical symmetry to be zero. But again, I can't prove that to you. But at least two of you in the room probably have an ample understanding of the way Gauss's law worked, that this has to be the same kind of thing. So no matter where you are in there, they'd experience a net force of zero. So unlike in King Kong versus Godzilla, where they're walking on the inside edges, not so much. Not so much. But okay, let's go back to what we're doing here. This is where I ask you guys to tell me the mass of the smaller sphere in terms of what's written here. We'll say the mass enclosed. You guys are sharp cookies. How would I do it? Nobody? You have the density. Heard part of what he said. Give it a shot. Figure it out. You have the density. It's a ratio problem. Figure it out. I would like you to get it all the way down to a nice, neat package. Try. There. Done. Is that what you got? If not, it's what you should have got. Density equals mass divided by volume. So this density also equals the mass enclosed divided by the volume enclosed. You don't take so long, guys. We don't have that kind of time. You multiply the volume times the density, you get the mass. It's the whole point of using density. That's why we said that the density is the same value everywhere throughout. That's all you need to do. The 4/3 pi cancels out. We get the ratio of the cube of the radii. That's it. That's what you could use. So our net force equals ma, and our net force is going to equal mass enclosed times the mass of u, we'll drop u down the hole, times g divided by how far away you are from the bottom of the hole, which is the center of the earth, how far away you are from the center of the earth. This has to equal the mass of u times a, because we're dropping u down the hole, and you're the one accelerating. Now, you should drop in the mass enclosed. All right, that's the next step. And you have an expression for it. So r cubed over r cubed, mg over r squared equals a. And before I go any further, just looking at our picture over here, if r is measured this way and is our displacement, what direction is the acceleration? Like, what direction are you being pulled? Is it this way or this way? All right. So this way. Is it clear that the force is in the opposite direction of the displacement? That suggests me a negative sign if we're going to compare the displacement to the acceleration. And by the way, when you reduce this, you get mg over r cubed times r. equals just A. Better yet, acceleration is the second derivative of displacement. We're just using r for the displacement, not x. That looks pretty much like the equation for a simple harmonic oscillator, doesn't it? Sure does. That's really it. If you want to find the period, you should do so. The period is 2 pi divided by c, which in this case will be 2 pi times the inverse of this and the square root, so r cubed over mg. Also, you have to plot force versus position. So if you want that right here, will be how you get force. You just multiply both sides by the mass of u again, and that gives you force equals minus mass of the planet, mass of u, g, over r cubed times r. So you're supposed to take and make a plot of force versus position. That's linear. So your graph would have to be linear until you get here. But once you get here, when r equals or is greater than r, this equation changes to this. Because we're outside the planet now. You have it's not a discontinuity, but you have a point with no slope. Right, it's continuous because there's a point there. What do they call something where there's no slope at a point? There's some word. You're supposed to know it. I don't remember it. Don't really care. But there it is. If it doesn't, it should. And the reason I bring it up is because, again, learned people. If you want to see what it looks like, you get the same answer if I ask you to find the period of an orbit that's right near the surface of the planet. If you don't believe me, remember how to do that? Right, it'd be net force equals MAC, mass of planet, mass of u, g, over r squared equals m of u, v squared over r. Solve that for v, but also 2 pi r equals vt. Sub it all in, and you get t equals 2 pi and square root of r cubed over mass of planet times g. They're the same. It's another link that circular motion and simple harmonic motion are strongly related. Also, we find that the period for the Earth is like 84 minutes. So if you put in the 5.96 and all that stuff, times 10 to the 24th, and 6.37 times 10 to the 6 meters, 84 minutes round trip, which means if you want to go from one side of the planet to the other using this method, it takes 42 minutes. And as I said, you could drill any hole, any straight hole through the Earth would have the same period. Therefore, the same point-to-point contact. So you fall down that hole, 42 minutes. Hopefully somebody's on the other side to catch you. If they are, good. You get out, somebody else gets in, they fall down the hole. 42 minutes, you're anywhere on the planet. I have a couple of world travelers in the room. Could you imagine 42 minutes at any point on the planet? I'm sure you can, because you probably had to spend hours and hours and hours getting somewhere on the planet. 42 minutes would be awesome, wouldn't it? And how much does it cost you in fuel? 0. You have to bore a hole through the Earth. So there are some energy consequences and evacuated of air make it so that it has no friction. But if it's through the center of the Earth, not so terrible, right? You wouldn't have to worry about the surface that you're going against. It's impossible, of course. But this also tells you that satellites are visible for about just under 42 minutes because you can't see them go across the entire sky. You can only see them from your field of view. So most satellites cross the sky in about 20 minutes because your field of view isn't a perfect half of the sky. It's only a portion of the sky.